Okay, welcome back to another talk by myself and with the help of Morgana. Tonight we're going to talk about the distance ladder, which is the way that astronomers use to measure the distance to planets, stars, and galaxies. And of course, I'm going to be asking questions. Stop it. And then I would like also to invite you to leave your questions in the comment even after the presentation has gone live. I can always come back and answer to them. Thank you very much. So welcome back. And tonight, as I said before, we're going to talk about the cosmic distance ladder, the scale of the universe, and why actually it matters so much for astronomers to measure the distance to stars, planets, and galaxies. So why do we care? Well, because first of all, by knowing the distance to an object, we can convert its apparent size to a physical size. And vice versa, if we know that an object is this big and we see it that small in the sky, we can infer its distance. It's like we are used to do this every time we see objects that we recognize, such as a car, and we see it very small, and we know cars are 2 or 3 meters long, so we can estimate that those cars are quite far away or close to each other. We do these kind of guesses every day. The other reason is that if we know the distance to an object or a star, for instance, and we can measure the brightness of that star, the apparent brightness of the star, knowing the distance, we can infer how intrinsically luminous is that object. And that is very important because then we can assess different ideas for what actually is powering that source of light. Is it a star? Is it an accreting supermassive black hole, for instance? Something else? Without knowing the distance, we may think that brighter objects are indeed closer, or that objects of similar brightness are equally distant. Consider the Orion Nebula. Pretty much all stars up there, they look the same luminosity, but if you look on the right here, in fact, the different stars in the Orion Nebula, in the Orion constellation, are pretty much at different distances. Finally, because light travels at a finite speed, if we look at an object that is very far away, indeed we are looking back in time. So to study the evolution of galaxies, we want to look back and very far away because we will see galaxies as they were forming at the early time of the universe. And just to cross our entire galaxy, it will take basically 100,000 years. So if you have an alien on one side of the galaxy looking at the Earth as we speak, he or she will actually see the Flintstones. He will see the prehistoric Earth. Now, when it comes to distances in astronomy, we are dealing with really big numbers. Indeed, that justifies the terms astronomical numbers. The moon is 384,000 kilometers away. The sun is roughly 149 million kilometers away. And the closest star, Proxima Centauri, is around 40 trillion kilometers away, which, if we don't know, a trillion is a thousand billion, so it's 4,000 billions kilometers away. So from now on, I think it's better to ditch kilometers and start thinking in light years, which roughly correspond to 9.5 trillion kilometers. And the closest star in that case becomes just between 4 and 5 light years away. The edge of the galaxy is 50,000 light years away. The closest galaxy is 2.5 million light years away, and near galaxies can be tens of millions of light years away. To understand distance in astronomy, analogies and visual example can help, but up to some point. One website that I like a lot to convey distances and also how empty is space is this website that I'm linking here, for which I'm going to show you the next video. So in this visualization, where 1 pixel is exactly the size of the moon, we can appreciate the size of the sun, and we can now start traveling across the solar system by scrolling with my keyboard. If I press the right button, I keep going and going, Now this was just 10 million kilometers. And you can see that space is indeed pretty empty. And it will take us still another few seconds to get to our first planet, which indeed is Mercury. And here we are. This is roughly 3.2 light minutes away. So if you thought this was quite slow, let's try to now go to the Earth at the speed of light. So if I press this button right here, I just go at the speed of light. So let's go faster. Oh, actually, we're going slower. This is actually how fast you can go in the universe. And indeed, it will take normally 8 minutes for light to reach us from the sun, and another 5 minutes for us at this moment to go to Earth on this screen. So I will let you play around with this in your own time, and I should go back now to my presentation. So in this So let's go back now to a nice question, and with another little analogy now to explain the distances between stars. If you make the sun as wide as a little 5p coin and you put it in London, and then you think of Proxima Centauri, which is our next closest star, and you make that also a 5p coin, where will you need to put it away from London to be to scale? Oxford, Edinburgh, Rome, or on the moon, Morgana? Oxford, yeah? No, that would be too close. You need to go as far away as Edinburgh. So indeed, space is pretty empty. I got a bit carry on with this analogy of the 5p coin, and I took it a bit further out, and I thought, okay, let's now imagine to build a model to scale of the Milky Way with just stars that are 5p coins. For that you will need pretty many 5p coins, 10 billion of them, like the number of stars in the Milky Way, and you need to spread them out on a disk that is the radius that is 17 times the distance between the Earth and the Moon. So I reckon that if you were to look at this 5p coin Milky Way in the sky, it will not look that much smaller or wider than the actual Milky Way. Now let's consider another analogy, which is that between galaxies. So now let's make the Milky Way basically as big as London. In that case, the nearest galaxy to us, which is Andromeda, which is also a similar size of the Milky Way, will be in Milan. And when it comes to the closest group of galaxies to us, the big Virgo galaxy cluster, that would be in Australia. Okay. Actually, if you are interested in better appreciating the vastness of the universe and its wide-ranging distances, you might as well come to the Armagh Observatory and Planetarium Astropark. Of course, once the present COVID-19 crisis is over. There you will find a solar system to scale model, as well as the so-called Infinity Hill, where you can travel from the Earth all the way to the most distant galaxies. And you can also try this out with our Armagh Observatory and Planetarium augmented reality application. Now, the range of distances to various objects in the universe, such as planets, stars, and galaxies, is so diverse that no one single method works to measure the distance to all the objects in the universe. Fortunately, measuring the distance to closer objects help us in calibrating methods to further reach out. And for instance, once we know the radius of the Earth, we can go and measure the distance to the Sun. Once we know the distance to the Sun, this will allow us to measure the distance to the closest stars, and so on. This is why we talk about a distance ladder. Now, the distance ladder in astronomy includes a whole variety of complicated methods. This graph is not here for you to understand, it's just to convey its complexity of all the different interconnected methodologies. So I'll just discuss a few. The first method I want to discuss is the so-called geometric parallax. The parallax method is something which everyone is actually very familiar with. It has to do with the change in apparent direction of an object with respect to a fixed background when you observe that object from a different position. In the case of your finger, the apparent change in the direction of your finger with respect to, for instance, a distant building is related to the distance between your eyes and your finger. So it basically has to do with the distance with the length of your arm. In nature, also animals use this trick. Owls use this method of the parallax to gauge the distance to their prey by moving their heads left and right and decide whether it's actually worth a try to catch them. Now, the parallax effect is smaller for distant objects, as you may have noticed by looking outside the window of a train. In this case, the movement of a train changes the position of the observer, which is you, and you can take the distant background as the clouds in the sky. The closest tree, they move very fast, whereas the further away trees or even the mountains, they appear to basically move very slowly or not at all. The solution for this actually is to wait a bit more longer until your baseline or your position really changes a lot, or to actually have sharper eyes and actually appreciate much smaller changes in direction. In other words, you need to go from using just your eyes to a telescope. When it comes to astronomy, in fact, we talk about not very much about degrees to separate different directions, but we talk about arc minutes and arc second, which are much smaller angles. An arc minute, for instance, is the typical limit of the human vision and corresponds to the angle subtended by a football nearly a kilometer away. An arc second, which is a much smaller angle, on the other hand, is the typical limit of a ground-based telescope, and is the angle subtended by a 5p coin if you were to place it very far away or closer to us. Morgana, what do you think? Should I put this 5p coin 10 meters away, 150 meters away, 2 kilometers, or on the moon? 2 kilometers. Well done. You're very good. This time you got it right. If you want to put it another way, you can use this image to appreciate how much smaller Venus and other planets that you cannot resolve with your own eyes is to the moon, are to the moon, which will look about right as it looks on the sky if you were to take this image on your screen and put it basically put your screen 6 meters away. Okay? Visualization, where 1 pixel is exactly the size of the moon, we can appreciate the size of the sun, and we can now start. Now let's start to climb the distance ladder. The very first step we have to do is to measure the radius of the Earth. This was first worked out by Eratosthenes quite a long time ago, who noticed that while on the 31st of June, which is summer solstice, the sun was directly overhead in the city of Cyrene in Egypt, on the same day it would cast a shadow of about 7 degrees in Alexandria. He correctly interpreted this was due to the curvature of the Earth, that the Earth was a sphere, and from this angle he deduced an estimate for the radius of the Earth of about 6,800 kilometers, which is pretty close to the actual radius of 6,371 kilometers. If you want to learn more about this, by the way, there is a nice lecture that our director Michael Burton gave a few days ago related to this and other historical achievement of the early steps of astronomy. Once you know the radius of the Earth, you can start exploiting this large baseline to, for instance, measure the distance to the first planets. Example, if you measure the apparent position of a planet with respect to distant stars if you observe it from different latitude. And this is something that was exactly worked out by Cassini and his colleague Richter in 1672 when Mars was at its closest to the Earth. Basically, Cassini sent Richter down in I think in French Guiana, to look at Mars, while it did comfortably so in Paris. The difference between their measurement was about 20 arcsecond, and from that they measured the distance between Mars and the Earth. What was the point of this? We only have the distance between the Mars and the Earth, so what do we learn from that? Well, from that distance, what Cassini worked out was actually the size of the solar system, starting from the size of the Earth orbit. Why? Because they knew about the Kepler's law. Johannes Kepler was a German astronomer that found three very important laws, called in fact Kepler's law. The first is that planets go around the Sun in elliptical orbit. The second is that they go faster when they are closer to the Sun. And the third, which is most relevant here, is that there is a very clear relation between the radius of these orbits and the time it takes for the planets to go around the Sun, which is shown here. Because we know that it takes roughly 2 years for Mars to go around the Sun and 1 year for the Earth to go around the Sun, with a bit of maths and knowing that when they are that closer between the Earth and the Mars, we have the distance that Cassini measured, then you can actually work out the distance of the Earth from the Sun and the radius of its orbit. And from that, you can work out then, knowing the period of all the planets relative to that of the Earth, what is the size of the entire solar system. This allows us to take a third step using the parallax method and move out to the nearby stars. Once we have the Earth orbit, we can exploit as a baseline, as a change in position when we look at stars, the different position of the Earth when it has it in June, say, to that the one that you have 6 months apart on the other side of the Sun in December. This allows to see a difference in the position of the nearby stars compared to very further away stars or galaxies. And typically this little variation in position in the sky or in direction of nearby stars is very small, and they are of about a few arcseconds at most. For instance, for Proxima Centauri, the parallax is 0.8 arcsecond. So the importance of actually having very good telescope is clear in this case, because you really need to resolve these more angles. For this, the best telescope in town is still the Hubble Space Telescope, which actually, happy birthday, the Hubble Space Telescope is 30 years old today. With it and other space telescopes, nowadays we can go halfway towards the center of the galaxy in measuring the distance to objects. Once you do that, you can actually start thinking about using the so-called standard candles. The concept of a standard candle is pretty simple. If you know the intrinsic luminosity of an astrophysical object, for instance of a special kind of stars, then from their apparent brightness you can deduce the distance. Clearly, the brighter the candle, or the brighter your special kind of star, the further away you can spot it, and hence the more useful it is as a distance indicator. There are many of these, and today I'm going to talk about only one about this standard candle, the Cepheid stars. Cepheid stars are actually variable stars. That means that their brightness actually changes with time. They are called Cepheids because they were first discovered in 1794 by John Goodricke in the constellation of Cepheus. One particular famous Cepheid star is very well known to us. What do you think is her name, Morgana? Is it Vega, Sirius, Polaris, or Pollux?
Polaris.
Polaris. Well done. That was good. And that's very good that it is Polaris, because Polaris is not that far away, and we know its distance, and thanks to parallax. So it will turn out to be quite a useful thing, as I'm about to explain. Now, I mentioned that Cepheids are variable, so they change their luminosity in time. So how can they then serve as standard for measuring the distance? Well, as it turns out, this is because they vary in a very rhythmic fashion over the span of a few days or months. This graph shows you an example On the horizontal axis, you have time, and as time passes, the star basically blows up or shrinks down. It becomes brighter, and draws a curve here that you can see, which is the luminosity, which oscillates up and down, up and down. So the higher the value on the vertical axis, the brighter is the star. Not only they vary over time, they also vary according to a very precise period luminosity relation. That is, when the star is actually brighter, they vary more slowly. When they are dimmer, they vary more rapidly. This allows you to estimate the distance to a Cepheid once you know the period, as long as you can calibrate this relation, as long as you know the intrinsic luminosity of one particular Cepheid that you know the period of. And that happens to be Polaris, for instance, which has a period of around 5.7 days and is 1,000 times more luminous than the Sun. And we know that because we know its apparent brightness, and we know, thanks to the parallax method, that is some 433 light years away. Now, Cepheids can be incredibly bright. They can reach almost 4,000 times brighter than the Sun, so we can spot them from pretty far away. In fact, they're also found in nearby galaxies, even quite further away ones. This allowed Edwin Hubble to find them in Andromeda, which is our closest galaxy, and showing that galaxies were actually moving, they were actually very far away. They were not just nebulae inside our Milky Way, they were external objects to our galaxy. But when Hubble used the Cepheids in Andromeda to deduce its distance, he already knew them to be distance indicators thanks to the work of Henrietta Swan-Leavitt, who was one of the Harvard computer girls, which included also Annie Jane Cannon. And it took quite some time for history to recognize the work of this particular lady and also of the other girls, computer girls, so-called. There is in fact also a very nice play about Henrietta Leavitt, which I suggest you can look up. Maybe also there are videos on YouTube about it, which is called The Silent Sky. In 1929, Hubble combined spectral measurements for the velocity of nearby galaxies through the method of redshift, which I will provide you with a link so that you can actually look it up, with his own measurement of the distance d based on the Cepheid variable, or so he thought, to actually derive a very important relation between the distance and the velocity of nearby galaxies, which is the so-called Hubble relation. This relation allows you, thanks to a very easy measurement of a velocity, to derive the distance of a galaxy. And you can do this measurement of velocity even to the furthest reaches of the universe. So you basically can use this method to find the distance to the most distant galaxies. Obviously, this also revealed the fact that galaxies are moving away from us, and in fact they are moving faster the more distance they are to us, and they are moving away in all directions. Now, the Hubble law actually strictly applies only to galaxies that follow the expansion of the universe. That is, for galaxies that really are far away and where the universe is expanding very, very fast. For more nearby galaxies, this expansion is pretty slow, as you can see in this graph. So for instance, if we have only galaxies that are, say, 16 million light years away as the distance of the Virgo cluster, which you can see here on the left, then galaxies move at around 1,000 kilometers per second, which is really a fantastic velocity, but is also comparable to their own velocity that they can have between each other, just because of the gravity that they experience, because they are in pairs or in group. And so these proper motions, they affect our measurements, and so you cannot use these galaxies to apply the Hubble law. And in fact, some of the most nearby galaxies even falling onto us. You know that, Morgana?
Yeah.
It's not going away, but it's falling onto us. You know which one? Is it the Whirlpool galaxy, the Large Magellanic Cloud, the Cartwheel galaxy, or Andromeda?
point to which one it is?
Now, I don't point to the solution. Morgana, you have to guess. Is it the Whirlpool, the Large Magellanic Cloud, the Cartwheel, or Andromeda?
The white one.
The?
The white.
The white one. Which is the white one? This is in the next slide. You're not allowed to cheat. Tell me. Whirlpool, Large Magellanic Cloud, Cartwheel, or Andromeda? Pick one. Andromeda. Well, yes, you're right. It is Andromeda, which is going to collide with the Milky Way in around 5 billion years. Thank you very much, Morgana. So we cannot use these objects to use the Hubble law, nor can we use these objects to calibrate the Hubble law in first place. We need to look for further away galaxies. This is why we have Hubble coming in play again. So here's an example of Hubble looking at a distant, more distant spiral galaxies and different places of the galaxy where Hubble spotted some Cepheid variables, which are outlined by these little green circles. Now, sometime while you actually measure the distance to one galaxy through Cepheids, you may actually have a supernova explosion in them. So here in the middle of this image, you can see the site of an explosion of a star, of a supernova that actually happened in 1995. This allows you to calibrate the intrinsic luminosity of that explosion. As it turned out, some supernovae, they have a constant intrinsic luminosity, and they also are so-called then standard candles. And in fact, they are so bright and much brighter than Cepheids that you can use them to go very far away. And my last slide, in fact, is to draw you to a very important result that was obtained using supernovae, is that by looking, very far away, using supernova, we found out that the Hubble law, which is the premise of which is that the expansion of the universe is constant, actually needs some modification, and that the universe is not expanding at a constant rate, but is in fact accelerating and expanding faster and faster and faster. And that got a Nobel Prize some time ago. So thank you very much for your attention, and I remind you that you can actually ask questions in the comments below, or you can leave them later on and I will try to come back to them later. Thank you. Then across the solar system.